Hello, in this video we're going to talk about AP Chemistry's topic 1.3, elemental composition of pure substances. So if you recall, a pure substance is a substance that has only one component particle. So for instance, elements only have one type of atom. So if you had a sample of carbon, every atom in a sample of carbon would be a carbon atom. If you had a sample of hydrogen, then every single atom in a sample of hydrogen would be a hydrogen atom. So they're pure substances because they only have one type of particle, one single type of atom. If you look at compounds, compounds have only one type of particle, but these particles are larger and they're composed of multiple elements. So like water is H2O. Every single molecule of water is exactly like every other water molecule. There's two hydrogens bonded to one oxygen. So because there's only one type of particle, one type of molecule, we say it's a pure substance, even though it has two different types of atoms within it. The particle that composes water, the particle that has the properties of water, is identical to every other particle that has the properties of water, H2O. Sodium chloride, salt, table salt. If you had sodium chloride, there's one ion of sodium for every one ion of chloride. So we say it's a pure substance. Now, a reminder that water is a molecular compound, a nonmetal bonded to a nonmetal. So that is a molecular compound, and that means that the particles of the molecular compound are called molecules. Salt, which has a metal bonded to a nonmetal, is not a molecule, because with ionic compounds, there's a sodium ion and a chloride ion bonded to another sodium ion, bonded to another chloride ion, and that process repeats over and over, creating a huge crystal lattice of alternating positive and negative charges over and over and over. And so these are not molecules. We just look at this ratio. There's one sodium for one chloride, and that's called a formula unit. It simply tells you the ratio of the ions in the ionic compound. So molecular compounds have molecules, ionic compounds have formula units. In both cases, though, the ratio of the elements in the compound is very important, and it's set. If you change the ratio, you don't have that compound anymore. So we're going to do a problem where we're going to find the formula for an unknown substance using an analytical technique. So in this particular problem, we are going to solve for two different things. We're going to solve for the empirical formula. And the empirical formula just tells you the ratio of the elements in a compound. We're also going to calculate the molecular formula for this substance. And molecular formulas are the actual numbers of atoms that are bonded together in a molecule. So for instance, hydrogen peroxide is H2O2. There are two hydrogens bonded to two oxygens in one molecule of the substance. So this is its molecular formula. However, the ratio between hydrogen and oxygen is 1 to 1. For every one hydrogen, there's one oxygen. So that's called the empirical formula. With molecular compounds, you have a molecular formula, which is the actual number of atoms bonded, and you have an empirical formula, which is the ratio of the elements that are bonded together. With ionic compounds, we're always talking about empirical formulas because it's always the smallest ratio of the elements that are bonded together. But with molecular formulas, it's important not just to know the ratio of the elements, but the actual number of atoms that are bonded together. So we are going to see how to calculate the empirical formula and molecular formula of a compound. So here's our prompt. There are 65 grams of an unknown compound, and it's decomposed. After it's decomposed, it is found to have 31.61 grams of carbon, 5.32 grams of hydrogen, and 28.0 grams of oxygen. If you add up those grams, they add up to 65 grams because we just broke it apart, and the law of conservation of mass says that after you break something apart, it still has to have the same number of atoms. So the grams add up. After the unknown substance is run through a mass spectrometer, its molecular weight is found to be 148.18 grams per mole. What are the empirical formula and the molecular formula of the substance? So first, we're going to calculate the empirical formula. And the empirical formula of the substance tells you how many moles are bonded to how many moles. In hydrogen peroxide, there's 1 mole of hydrogen for every 1 mole of oxygen. So formulas are always mole ratios, which means we need to convert our grams into moles. That's got to be our first step. So our first step is to convert each one of these grams of elements into moles of the elements. So 31.61 grams of carbon. There's 12.01 grams of carbon in every 1 mole of carbon. And if you do the math on that, you will get 2.63 moles of carbon. So that's how many moles of carbon are in this unknown substance. We're going to do the same thing with the hydrogen and with the oxygen. So for hydrogen, there's 1.01 grams of hydrogen in 1 mole of hydrogen. And that gives us 5.27 moles of hydrogen. So in the 65 grams of unknown, there's 5.27 moles of hydrogen. And lastly, we need to convert oxygen. So 28.07 grams of oxygen. There are 16.01 grams of oxygen for every 1 mole of oxygen. And if you do that math, you'll get 1.75 moles of oxygen. So here's how many actual moles of each element are in this sample. But we want to know the ratio of the elements. In other words, what's the mole ratio of carbon to hydrogen to oxygen? Technically, it is 2.63 to 5.27 to 1.75. But formulas need whole numbers. So we're going to divide each of these by the smallest of the 3 and figure out what the whole number ratio is. So the smaller of the 3 moles is 1.75. And remember, with ratios, if you divide every number by the same number, the ratio is the same. So if we do this, we get 1.5 for this one, for carbon. We get 3.01 for the hydrogen, and we get 1 for the oxygen. So now we see the mole ratio is 1.5 to 3 to 1. Now notice we still don't have a whole number ratio here. 3.01 for all intents and purposes is 3, so I'm just going to make that a 3. But we still don't have a whole number ratio, 1.5 to 3 to 1. So what are we going to do to get a whole number ratio? Well, what could we multiply all 3 of these by in order to get a whole number? Well, these are already whole numbers, so if I multiply them by any whole number, I'll still have a whole number. But 1.5 is not a whole number. What could I multiply 1.5 by to get a whole number? Well, if you answered 2, you're correct, because 1.5 times 2 will give me 3. So I'm going to multiply all of these by 2, because again, if you multiply a ratio by a constant, you still get the same ratio. So 3 to 6 to 2. So there's our whole number ratio of the elements in this compound, C3H6O2. This is the empirical formula, because it's the smallest whole number ratio of the elements in the compound. So the empirical formula is simply changing our grams into moles and then figuring out the whole number ratio of the elements in the compound. Now the question is, does the molecular weight of this empirical formula add up to 148.18? So what we're going to do is we're going to add up 3 carbons, 6 hydrogens, and 2 oxygens and figure out the molecular weight of this empirical formula. If you do that, 3 times 12.01 plus 6 times 1.01 plus 2 times 16, you get 74.09 grams per mole. So obviously 74.09 is not 148.18. So this empirical formula is not the actual numbers of atoms that are bonded together in the real compound, because the real compound adds up to 148.18. So what we want to figure out is how many of these empirical formulas are in the compound. So the compound could be C3H6O2, which we know it's not because the molecular weight is not correct. It could be some multiple of 3, 6, and 2. So C6H12O4, C9H18O6, or continuing on. Notice these ratios are still a 3 to 6 to 2 ratio. So we need to figure out which one of these adds up to 148. So all we're going to do is we're going to take the total molecular weight, 148.8 grams per mole, and divide that by the molecular weight of the empirical formula, 74.09 grams per mole. And if you do that, we get a factor of 2. In other words, it takes 2 empirical formulas to add up to the molecular weight. So what that means is we're going to take our empirical formula and multiply each of the subscripts by 2. And that will give us C6 H12O4, which will be the molecular formula of this compound. So this compound has 6 carbons bonded to 12 hydrogens bonded to 4 oxygens, and that's one molecule of this compound. So that's just a quick reminder of empirical molecular formulas. Just one more reminder that if you're given percentages of the elements in a compound, for instance, let's say something's 48% carbon and 52% oxygen, and you want to figure out the empirical formula, just change your percentages to grams, 48 grams and 52 grams, and then proceed just like we did in this particular example. Convert your grams to moles and figure out the mole ratio. So I'm going to stop there. I hope that this was helpful. If you have any questions, please let me know. I'll be happy to help you out. Good luck.